But next up, we have Tim Livengood, who will be speaking about SNFLER, Surface Neutron Flux Lunar Empirical Ratio.
Hi, this is Tim Livengood. I assume you can hear me. So SNFLER is exactly what it says. Our logo is in fact our concept of operations. Next slide, please. The idea that I want to get at here is we have a problem with a lot of ambiguities. We've observed a diurnal variation in the hydration of the regolith from several channels in near-infrared, ultraviolet measurements, ground-based spectroscopy. A big open question is whether that's a monolayer, a poorly defined term in this context, or whether we're looking at just the top of a layer that goes deeper that's hydrated. We attempted to probe this with LEND on LRO, which probes deeper into the surface, and found a diurnally variable neutron flux with a maximum effect near dawn, and so a different pattern than what's seen with the optical methods. The amount of water that would be implied to change in the regolith from dawn to mid-afternoon is small, and so it requires high signal to noise to get at it. But we're talking about this happening at low latitude, which is an interesting prospect. And even at the small amount of water we're talking about here, to account for this by actual transport over the surface of water is a real conflict with expectations for a surface-bounded exosphere and surface ballistic transport. Next slide, please. So SNFLER is intended to resolve the issue. The way that a neutron instrument works is you have neutrons are generated in the surface by cosmic ray flux, and you have a moderated spectrum. But if there's hydrogen present in the soil, it moderates it even more and gives you a local suppression in the epithermal flux of neutrons and a local increase in the thermal neutron flux. And what we'll be looking at with SNFLER would be the ratio between those two things. Now, if you look on the right there, uh, the regime that's relevant for the amount of neutron suppression or epithermal suppression that we saw with LEND is down at a very low level. It's not unmeasurable, it's just very low, and it requires a sensitive system to go at it. So next slide, please. And so here's an example of how we actually generate, or not we, how nature generates the neutrons with a cartoon example of what SNFLER looks like, a multi-detector system with both thermal and epithermal neutron detectors arranged so that they don't shadow each other and so that they compensate for any anisotropy in the angular sensitivity of the different detectors, and then just having multiple detectors to have to raise the count rate. It compensates for some systematics that have been a problem with other
2 minutes.
Sensors that we've used. How much? 2?
2 minutes.
No problem. First of all, by looking at the ratio between thermal and epithermal neutrons, we compensate for any variability in the cosmic ray flux. Also, changes in scattering cross-section within the regolith due to temperature have about the same direction and not quite the same magnitude in both thermal and epithermal. So by ratioing them, we compensate for that. I've already mentioned the multiple detectors give us high signal to noise, high detection rate, and compensate for individual variability in the detectors. And lastly, we're not planning on going anywhere. The idea is to deploy onto the surface and leave it there so that nothing can change but the amount of water or hydrogen that may be in the regolith below us. Next slide, please. And so our primary goal is to look at the variability with time, but also, and where it's overkill for this purpose, but to establish the absolute water abundance at the site by modeling the neutron flux that we would expect in each energy range in order to estimate that. But the primary goal is determining the amplitude of the variability, and that we can do just with the ratio of the detectors as a self-calibrating system in that sense. Next slide. And that's my last one. The idea is just either suspended over the surface, for instance, from a cable, on a spar that extends out from a lander, or just eject it from a lander and let it sit on the surface. with a reflective outer shell to keep the detectors cool. And not as many detectors as you see here. That was a little getting carried away, but basically to be a very a boring measurement, because measuring things should never be exciting. Analyzing it should be exciting. Thank you. I'm done.